All right, so what we're going to do now is we're going to look to see whether or not the redox reaction we've identified is spontaneous. When we say a reaction is spontaneous, it means it can happen without us putting in energy. So in other words, it has a positive voltage. And what you can do is you look in your table of standard reduction potentials, and if you see that the voltage is positive, or the overall voltage is positive for the reaction you've identified, we say that's spontaneous. It'll just happen. The other reactions that aren't spontaneous, we can make happen by putting in energy, putting an electric current through or providing some source of energy. That means the reaction will happen. All right, so let's figure out if a reaction is spontaneous. Let's take a look at sodium metal, and the sodium metal is going to be oxidized, so it's going to release an electron. And let's pair this up with fluorine. So we've got fluorine, and we're going to give fluorine electrons, and that's going to make fluoride. And so this is our reaction. We wonder if these two reactions paired will make a spontaneous redox reaction. So first thing we have to look and say, is this thing even a redox reaction? Well, the sodium's losing an electron, and the fluorine's gaining an electron. So yes, it's a redox reaction. And it's a redox reaction that will work, because one person's losing and the other's gaining. If we had two species losing electrons, that's not going to work. Or two species gaining electrons, that's not going to work. We've got one losing, one gaining. Is this spontaneous? Well, it's easy to tell because you have access to a standard reduction potential table. So you look at the back of your book, and you look at your standard reduction potentials, and you get the numbers off the standard reduction potential. So I look here, and I see that the reduction of fluorine nets me 2.87 volts with, under these conditions. And then I have to look for the oxidation of sodium. And I see sodium in there. It's way down the list. And I see this reaction listed. I see sodium getting an electron and becoming sodium metal, so sodium solid. And I find to do that takes 2.71 volts. Is this the reaction I use? That's the one in my table. Can I use this one? No, I have to do what to this one? I have to reverse the reaction. And if I reverse the reaction, no longer will it take 2.71 volts. What will it do? It'll net 2.71 volts. So what I did was I found this in the table, and I reversed it for the reaction I want. An oxidation has to be paired with a reduction. So having this one, where sodium is reduced, isn't helpful. I need something that's going to be oxidized to match with the fluorine that's reduced. I add up the voltage. And I see that this reaction, not only is it spontaneous because of the positive voltage, it's quite energetic. This would make a great battery, except for the fact that having solid sodium around is kind of explosive, so that really wouldn't work. So, what is the rule for a spontaneous reaction? It's a simple rule. We can look in the chart, identify the two half reactions, and then sum their potentials to see if we get a positive number. If the voltage is greater than 0, great, we have a spontaneous reaction. Or we can look at the chart and we see that any number above on the left, any reaction above on the left, will automatically work with a reaction below on the right, because that means that the higher number will be the favorable reaction. So anything above on the left will spontaneously react with anything below on the right. And that's just a rule of thumb. So any species above and to left of chart, and I'm talking about our chart of standard reduction potentials, will oxidize. In other words, it'll take the electrons from anything below and to the right. So if I look at this chart and I find one species above on the left, it will spontaneously react with any species that's on the other side, right, the reduction side, on the left. If one of the species is below, for example, if I want to use, let's say, gold 3+, and the species I want it to oxidize is above on the right, it won't oxidize it. It takes too much energy going in the other direction. So that's a little trick that can help you. What it really comes from is identifying what the potential is for each half reaction, and then summing the half reactions in the correct, written correctly. We still need to do this, however, if we're asked for the actual voltage of the reaction. Right? There's no way to know what the voltage of the reaction is before taking the voltages of the two half reactions and putting them together. Okay? It doesn't matter if we need to go through this reaction twice, as we would have to, obviously, to balance the requirements of fluorine. Right? Fluorine needs 2 electrons. Each sodium only liberates 1 electron. This reaction will have to happen twice for this one. It doesn't double the voltage. It's still the same voltage because the voltage is on a per atom, per electron basis. Okay? Yes?
Mr. Blubber, do you know how lithium-ion batteries work? And if so, could you explain to me this?
Why would lithium make an excellent ion to use in a battery? Take a look at your table of standard reduction potential. Why is lithium such an excellent choice for batteries?
It's at the very bottom.
It's at the very bottom, and when we when we oxidize lithium, what does it net us? Well, when we oxidize lithium, right? Yeah, so positive 2.4? 3.0. 3.0, wow. So lithium is giving us a lot of voltage from its oxidation. And that's why lithium is such a popular thing for batteries. All right, so your homework